Welcome to Thermodynamic Property Relations. This chapter takes us beyond basic concepts and into the powerful relationships that connect various thermodynamic properties together. Think of it like a map. When you know where you are, these property relations help you find other unknown points without needing to measure everything directly. Understanding these relations saves time and gives you deeper insight into how pressure, temperature, volume, entropy, and energy interact in real systems. It's like unlocking a shortcut in thermodynamics, making complex problems much easier to solve. By the end of this chapter, you'll not only be able to calculate properties more efficiently, but also appreciate the beautiful symmetry hidden in thermodynamic equations.
1. Mastering thermodynamic property relations. Let's start with what you will achieve in this chapter. Every learning outcome here serves a practical purpose, helping you calculate and understand properties that are otherwise hidden. You'll learn to develop connections between thermodynamic properties so you don't always need to rely on experimental measurements. For example, Maxwell relations will become your go-to tool for transforming complex equations into something simpler. We'll also cover powerful tools like the Clapeyron equation, Joule-Thomson coefficient, and departure charts, which are essential when dealing with real gases, not just idealized systems. By the end of this chapter, you won't just memorize formulas, you'll understand where they come from and how to apply them confidently in any thermodynamic analysis.
2. Grasp the power of partial differentials. Let's make partial differentials less intimidating. In thermodynamics, every system can be described by just two independent intensive properties. Once you know these, everything else can be calculated. The total differential equation you see here, dz equals mdx plus ndy, is simply a way to express how a property changes when you slightly tweak two variables. It's like describing how the taste of a soup changes when you adjust salt and spice. You'll also learn about reciprocity and cyclic relations. These are built-in checks that help you avoid mistakes in derivations. They're like the spell check of thermodynamics, making sure your equations always stay consistent and logical. 3. Make thermodynamics simpler with Maxwell relations. Let's simplify your thermodynamics toolbox. Maxwell relations are like shortcuts, powerful identities that save you from complex derivations. They are born from Gibbs relations, which link energy forms like internal energy, enthalpy, Helmholtz, and Gibbs free energy with measurable properties. These elegant equations connect temperature, pressure, entropy, and volume. Instead of re-deriving property changes every time, you can just apply these ready-to-use relations, like having a cheat sheet built right into thermodynamics. Most importantly, Maxwell relations help you calculate entropy change indirectly. When you can't measure entropy directly, Maxwell relations translate measurable changes in pressure, volume, or temperature into useful answers. Let's make phase changes easier to predict. The Clapeyron equation gives you a direct link between enthalpy change and the slope of the phase boundary on a pressure-temperature diagram. Instead of measuring complicated phase behaviors, you can use this equation to predict how pressure changes with temperature during vaporization or condensation, key for understanding boilers and condensers. At low pressures, we simplify it further with the Clausius-Clapeyron equation, which lets you calculate vapor pressure using just temperature and enthalpy of vaporization. This shortcut makes phase transition analysis much faster, especially in real-world engineering problems. 5. Master energy and entropy calculations with general relations. Let's make your thermodynamic calculations more powerful. This slide gives you general relations for internal energy, enthalpy, entropy, and specific heats, covering both constant volume and constant pressure processes. Instead of memorizing separate equations for every case, you'll see how changes in temperature, volume, and pressure are all connected. Think of it like having a universal formula sheet that works in many situations. You'll also meet two helpful property terms: beta, volume expansivity, and alpha, isothermal compressibility. These capture how a material reacts to changes in temperature and pressure, making your predictions more accurate, especially for real gases and liquids. With these general relations, you'll be able to handle complex problems with ease, using the right formula for the right situation.
6. Understand cooling with the Joule-Thomson coefficient. Let's uncover what happens when gases flow through valves or nozzles. This is where the Joule-Thomson coefficient comes in. It tells you how temperature changes when pressure drops during throttling. Here's the key takeaway. If μJt is greater than 0, the gas cools down. This is how your fridge works. For ideal gases, μJt equals 0, meaning their temperature stays the same because they don't have intermolecular forces. You'll also see how this coefficient links back to specific heat. This expression helps you predict cooling or heating effects during throttling, making it an essential concept in refrigeration, liquefaction, and gas processing industries. 7. Correct for real gas behavior using departure charts. Let's discuss how to handle real gases. Real gases don't follow ideal gas laws perfectly, especially at high pressures or low temperatures. That's where enthalpy and entropy departure charts come in. These generalized relations allow you to adjust your calculations by adding a correction term using factors ZH and ZS. Think of it like adding a reality check to your ideal gas equations. By applying these corrections, you can accurately calculate changes in enthalpy, internal energy, and entropy in real gas systems, helping you avoid costly design mistakes in compressors, turbines, and refrigeration cycles.
8. Focus on what really matters. Key applications. Let's finish strong with a quick summary of why these thermodynamic property relations are so useful. Each tool you've learned has a clear purpose. Maxwell relations help you simplify complicated entropy calculations. The Clapeyron equation makes phase change enthalpy predictable. General relations allow you to find internal energy, enthalpy, and entropy from data you can actually measure. The Joule-Thomson coefficient explains temperature changes in throttling, helping in refrigeration systems. And departure charts keep your calculations realistic when dealing with real gases. Think of these as your essential shortcuts in thermodynamics, designed to make your analysis smarter, faster, and more reliable.